This is another truss where we're asked to identify whether or not it is determinate, check stability, and check for any zero force members, along with finding forces in HG, HC, and BC, which are here, HG, HC, and BC. Since we're only asked to identify forces for only a few members, this indicates that we're going to use method of sections, not method of joints, and we'll only solve for what we need to for this problem. Now, there's many ways to approach a problem like this, and it really is up to the person solving it which section cuts they use and which methodology they use, whether it's cutting out whole sections or cutting out some joints and where those cuts are. So this is one possible solution. Our first step is always to draw the free body diagram, and the free body diagram helps us because we can now start to fully understand the problem, and we can identify every and all forces that are on this problem. And we'll also start to modify this diagram as we go. We'll show where our section cuts are on this diagram. So it's good to have a second diagram so that we don't really cause too much information on that first one. So we'll draw all our truss cords in, and we should add our forces as well. We have these vertical forces at each joint location along the top of this top cord, and each of them are 600 pounds. Excuse me. And this is a pin on one end, a roller on the other. That means that we have two reactions on the pin end. We have a vertical component of that force. This is RAY. And we have a horizontal reaction force, RAX. And at the roller end, we only have a vertical force, REY. And let's put our joint names on this. So we've got joint A, J, B, I, C, H, D, G, F, and E. And then we have these same 4-foot dimensions. They work for the top as well. I should add this dimension here though. 3 feet. Okay, so now that we have this fully drawn, we can start to answer the problem here. Question A is static indeterminacy, and this is equal to B plus R minus 2J, where B is equal to the number of members, and a member spans between joints. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 members. R is the number of reactions. And here we have 1, 2, 3 reactions. And J is the number of joints. And if we counted those, we'd see 10 joints. So SI is equal to B plus R minus 2J, and SI is equal to 17 plus 3 minus 2 times 10. And this is SI is equal to 0. And therefore, this is a determinate truss. And determinate means that we can solve for everything in this truss with only our equations of equilibrium. We don't need to use any fancy analysis techniques. Part B is asking for stability. So we'll look at our reactions. Are all our reactions parallel? Well, RAY and EY are parallel. AX is not. So not all reactions parallel. And not all of them are concurrent. So concurrent reactions mean they all pass through the same point. But since these are parallel to each other, these two of the three, they'll never touch, so they aren't concurrent. And this satisfies our stability requirements for equilibrium. And then we can say that SI is greater or equal to 0. So we do have enough supports. And finally, we have no internal collapse mechanism. So therefore we can say we are stable. This is the simplest of trusses, really. It's just a collection of triangular elements. And a triangular element has resistance from collapse. The diagonal force component comes into play to provide stability. So we do have a stable truss. Once we have that, we can begin looking for zero force members. And so part number C here is zero force members. And if we look at what a zero force member is, or how we find one, we can say that we have two cases we've identified. Case number one. Case number one consists of two members framing into the same joint. Let's call this joint A. We have B and C. And there's no force at that joint, and there's no reaction at that joint, and the two members are collinear. That means they both have to be zero force members. And then we have case 2. And in this case we have three members framing into the same joint. Let's call this joint A, B, C, whatever joints we want to call them. And then we've got another member goes down to joint D over there. Now joint member CA and AB are collinear, and member DA is non-collinear. There is no external force or reaction at A, and this means that member AD is a zero force member. And we showed why in class. We sort of proved that the equilibrium cannot be established if those weren't zero force members. So at this point, we can go back to our original drawing, and I'll just slide this down a bit, and let's look at what we had in terms of our free body diagram there. And we can see that we don't have any case 1 scenarios, because all of the times where we only have two members framing in, we have an external load, a J and an F. However, if we look at joint B and joint D, we have two of the case 2 scenarios happening there. So if we make a little table, joint, and then member, and then case, we could say that at joint B, we have member BI, that is case 2. And at joint D, we have member DG, that is case 2. So the joints B here, this member here has to be zero force. And at joint D, this member here has to be zero force, because of a rule established with case 2. And those are all of the zero force members in this truss. Now problem D asked us for the force in HG, force in HC, and force in BC. And to do that, we'll employ the method of sections in a way that seems relatively efficient to me. So the way that I've solved this, first off, I'm going to require the vertical force component at E, REY. So we'll find REY. And this will be done with sum of moments about point A is equal to 0. And therefore we have REY times 16 feet, rotating it counterclockwise, so that's a positive value, minus 600 times 4, minus 600 times 8, minus 600 times 12, minus 600 times 16 is equal to 0. So those are all of our vertical forces at distances away from point A. So 600 times 16, 600 times 4, and the ones in between. If we solve for REY out of that, we end up with 1,500, or this is in pounds, 1,500 pounds going up. So once we have that, we're able to move on. Now, knowing that we had to find REY comes from experience. or from starting the problem and then seeing that we're missing something that we could have found with global equilibrium. So because I've already solved this, I knew that I needed to find REY, but I found that out after drawing the following diagram. So I'm going to say we're going to cut through location AA, which I haven't identified yet. So let's identify location AA here on our drawing. If we give AA here, and we cut straight down through those members, and we draw a free body diagram for that, we can see that, let's see if I can keep that on here, somewhat, okay. So if we cut through AA and then we draw our free body diagram, we can see that we would have needed REY if we didn't have it already. So 1, 2, 3, 4. So I'm going to draw the right-hand side. Now this is the free body diagram of right-hand side of the cut. So at this cut we had 600 and 600 here. We had a known value that we calculated for REY is equal to 1500 kilonewtons. We have a vertical distance here of 3 feet, and then we have a distance in the horizontal direction of 4 foot and 4 foot. So this is joints E, F, G, D. Over here we have joint H, it's on the other side of our cut, and joint C. So when we made that cut, we intercepted member GH or HG. So let's put our force, and that is pointing right at H there. And this is F, GH. And then we also cut through FGC, or member GC. So we've got a force here. This is FGC, and it's pointing right at joint C. And finally we cut through a joint here, and this is FDC, and it's pointing directly at joint C. Now of these, our interest lies in force GH, because we can see that we are not looking for a force in GC or DC. So let's exclusively try and find force GH, and we can find that by taking the sum of moments about location C, and then DC and GC both cancel out because the moment arm is 0. And then we can see here that's why we needed REY. So let's find FGH. So at this point I guess we don't need this diagram. We can find FGH by taking the sum of moments about location C and setting that equal to 0. And then this force traverses through C, and this force also does. So we will have a force FGH times a moment arm of 3. And that's trying to rotate it counterclockwise, which is positive, minus 600 times 4, trying to rotate it the other way, so it's negative, minus 600 times 8 is a negative moment, plus 1500 times 8 is a positive moment, and that's equal to 0. And this 1500 is our EY, the 600s are our vertical loading. If we solve for FGH, we can say that that is equal to minus 1600 pounds. So FGH is equal to 1600 pounds in compression. Since it came out as a negative number and we drew it tension positive and then we put it in our equation based on a sign convention, it came out negative. We found that FGH is 1,600 pounds in compression. It came out negative, meaning it's factored into our equation the wrong going the wrong direction. Once we have that, we're ready to make a second cut where we can identify some more of our forces. So let's come back to this drawing here. And now I'm going to say I would like to cut through a location I'll call B. Once again, this method is subjective in how you get to your end result. This could have been solved excuse me. This could have been solved with a simple cut that goes through BI, or goes up along here, and then we identify member HC as well. But instead of that, we're going to cut through the location BB and try and get the force in a member. Which member would this be? In member BC. So we're looking to get the force in this member here, in BC. We've already found the force in HG, and later we'll get the force in HC. So we're going to take that cut there. We're going to say, let's cut through BB and draw a free body diagram. So cut through BB. And if we draw a free body diagram for that, it's not too hard. It's similar to the last one. So we're going to go over 1, 2, 4. All the way over to there, down 3, repeat that. Alright, so here we've got our external force here, 600 pounds at joint H. We've got 600 pounds at joint G. We have 600 at joint F. We know our reaction force here, REY, is equal to 1,500 pounds. This is joint E. There's a height here of 3 feet. There is a distance in the x direction of 4 foot, 4 foot, and 4 foot. Beyond that, we have joint D, we have joint C. Somewhere over here, 4 feet away, and here, 4 feet away, we have joint I and joint B. So, we made a cut through this top member here, and that exposed a force. And that force is FHI. And we don't know it, so we draw it as positive in the tension direction. There's a force been exposed here as well. This is the force FCI, and it points up at joint I. And another force here, and this is a force that we're interested in. This is FCB. So once we have that identified, we don't need this drawing for now, and we can go to our free body diagram that we just drew and try and solve for the missing force component with as simple of a way as possible. So here, I'm going to suggest that we would take the sum of moments about location I to find force CB, because FCI and FHI both traverse through that point. So to find FCB, which is their goal here, we will take sum of moments about I and set that equal to 0. And this will give us REY times the distance away, 12 feet, rotating it counterclockwise, the positive direction, minus FCB times 3 feet. This will be rotating it clockwise, which is negative, minus 600 times 4, clockwise as well, minus 600 times 8, minus 600 times 12. And all of that is equal to 0. And then if we substitute in our values, we could say that minus FCB times 3 minus 14,400 plus 1,500 onto 12 is equal to 0. And FCB is equal to plus 1,200 pounds. So FCB is equal to 1,200 pounds in tension. And since we don't care what the force in member CI or HI is, we don't need to continue with this particular section cut. So now let's see what we know and what we don't know. Let's go back to our original drawing here. And now we know this force and we know this force. Well, if we make a new cut that just cuts out joint H, and we'll call that CC, then we can directly solve for the force in HC with little difficulty. So now we will cut through CC as identified in our drawing. And then once we have that done, we can draw a free body diagram for that cut. And that free body diagram will simply look like a particle equilibrium problem. We have joint C. We've got the members framing on either side, and the vertical member here. Or sorry, not joint C, joint H there. So this is joint H. Onto joint H we have a vertical force of 600 pounds. And then coming out of joint H we have a force FHI. And we have a force on the other side, FGH. And actually, let me just fix that up here, because we know what FGH is already. We know that FGH is a compression force. We've already calculated that. So that was our first cut, found FGH is equal to 1,600 pounds. So since we know that it is acting in compression, we'll draw it as compression. It's a known value, it's drawn as it is. And finally we have FHC. And we don't care what FHI is, so it's quite easy for us to find FHC. We can take sum of forces in Y and set that equal to 0. And therefore we will have minus FHC minus 600 is equal to 0, so FHC is equal to minus 600 pounds. FHC is equal to 600 pounds in compression. So at this point, we have now solved for all of the unknowns that we were asked to solve And we are simply left with summarizing our problem. So, as with any problem, we're going to want to provide a summary diagram showing the values that we calculated on our drawing itself. So here we would draw our truss out, and then we would add to it the values that we know and the values that we're interested in. So we found our EY, so we added to our drawing. We didn't find A, so we can't add anything there. We identified a zero force member here and here. And then beyond that, we found that we have a compression force of 1600 in HC, a compression force of 600 in, or this is HC, in HG there's 1600, and a tension force of 1200 in BC or CB. And at that point we can say that we've satisfied the problem and we're finished with our work.